Hi everyone, very good morning. Welcome back to Boost Studies, that calculus series. We've been doing that something related to the Calc 2, with the calculus with analytic geometry 2, the material, especially with when it comes to that finding that area under the curve, and then when those particular area being rotated around a certain axis. It may be y-axis, x-axis, or any axis parallel to y or x, or not the slant one. We're not going to talk about the slant one at this stage, because that we don't have to worry about those things at this stage, because that we are trying to lay down a good foundation for us to get a clear idea about what the this analytic geometry would be at the end of the day. Even with that, the Calc 2, that there is a section called that the volume. Volume section is kind of like a little bit harder, because in the volume section that we are trying to find out that the volume generated by volume of a certain three-dimensional figure generated by rotating a two-dimensional plane about a certain axis. Either may be y-axis, x-axis, or any axis parallel to those two axes. And in addition to that one, sometimes they might gonna give you like some kind of like a three-dimensional figure, and then take out certain part and say, hey, just find the volume of that leftover, like that. Or sometimes you might be given like some kind of the ball, and they might gonna pump some kind of a liquid or water or any kind of air or liquid, doesn't matter. With such kind of a scenario, that again they might gonna ask you that how to find the volume if that has the the level of that particular gas or that liquid or the that fluid has risen up to certain level. So those kind of questions and something like that. I would like to go through something like that today and see that, especially that when it comes to the point in the volume, we know that we are dealing with three methods: disk method, washer method, and shell method. Disk, washer, shell. It depends on the way that how they've been set up, that we have to utilize the either one of these or two of them at least, because the washer method is an extension of the disk method. So they both have the same thing. In a disk method, there's a disk, there's no hollow something inside in the middle. But when it comes to the washer is pretty much a disk, and the middle part has been taken out. So it's a washer and the disk kind of the same thing. But when it comes to the shell one, it's kind of like a different way of doing things. Okay. Anyhow, let's look at this example to get a clear idea about what's going on. Okay. Let's see. I'm going to write this down very clearly on the question. Okay. And then try to answer this one. This Q. Q stands for question. A bead is formed by removing a cylinder. Cylinder of 3R. This 3R, simple R, okay? 3R. That means that cylinder is characterized or given with the aid of its radius. The radius. This whole thing is the radius of cylinder, okay? Make sure, not only R, 3R, okay? 3 simple R. From the center of a sphere of 4 capital R, see, 4 times capital R. That means this is not merely that the radius, the whole thing is the radius of the sphere, because the sphere has been characterized by the radius, okay, by the radius. Then what they're looking for, find the volume of the bead. the bead with r equals when with r equals 2 and when r simple r equals 1 by using first one the washer method, the other one shell method, sorry, washer method, the shell method. So that's the question. You have to find the volume of the bead that has been formed by taking out a certain cylinder with a certain radius, which is 3 simple r, 3 times simple r, from a sphere with a certain radius, which is 4 times capital R. So R, okay, capital R here, note this radius of sphere is greater than that of the cylinder. Make sure that the sphere has like a larger radius than that of the cylinder. That of the cylinder. Okay, you know, read. You can read it. No? Okay, how to get this done? We have 2 methods to be utilized here, washer method and the shell method. Let's get on to the washer method first. And then before we're going to do anything, we have to draw this one. Okay, let's draw this one. Make sure the radius of the cylinder as well as the sphere is not merely r and simple R and capital R. They are 3r and 4r. 3 simple R and 4 capital R. Okay, let's draw this one. See? Okay, that's the sphere. Trace the whole thing. Okay. See, this is the sphere. 3-dimensional sphere has been drawn on a 2-dimensional plane. This is the way how we're going to see that one. It looks like a circle, but it's not a circle. It's a 3-dimensional figure. Okay, 3-dimensional figure. You know that. From this one, you have taken out a cylinder from the center. See, this is like my axis of symmetry. Axis of symmetry. See, this one. If you want, I can call this on my y. Another way, that's called axis of symmetry has been abbreviated as axis of symmetry, AOS, or you can simply say axis of rotation, AOR. degrees of rotation. And for my convenience, I'm going to take this one as a x-axis. See, this is x. So there's a cylinder. See, cylindrical shape. See, cylinder. We go to the other side like this. See, like that. That cylinder has been taken out. It has a radius. See, if you go ahead and look at this one, from here to here, the radius of the, from here to here, radius of the sphere. From here to here, radius of the cylinder, and this side as well. For the sphere, it can go either way, even this length, same as this length, same as this length, same as this length. For our convenience, okay, I'm going to write here something. Radius of sphere, the way that they have given, it's 4 times capital R. Since 4 times capital R, I'm going to use a different letter R prime to indicate sphere. Don't use R, because R has already been utilized for this structure. This is a little bit tricky question. Now, pretty much the same way, radius of cylinder, which is 3 simple R, 3 times simple R, that's my simple R. I'm going to write this wherever that, even in the middle of some places, sometimes, see, I prefer to write capital R here to distinguish that from simple R, because simple R look like sometimes V. Okay, make sure this is simple R, okay? I'm going to denote this by R prime, see, the whole thing. So in another way, this is R prime, simple R prime, this is capital R prime. See? This is the bead. Bead is hollow. There's a very cylindrical hollow in the center. Okay, the rest would contain the material. Okay, you have seen the beads. You know how it looks like. This is how it's being created at the end of the day. Okay. This is the way. So if you use the shell method, or if you use the washer method, first one is the washer method. What that means, you can remember, forget about this one for time being, when you have a situation like this, okay, you have something, okay, I would say some kind of a, something like that kind of a curve, see, this is x-axis, this is y-axis. You've been given the equation of the function, see, f of x. For my convenience, I'm going to say x squared, okay? Like as an example, let's say that I'm interested on knowing that getting the area under the curve from x equals 1 to 2. I'm interested in this area. See, you know how to find the area. In order to find the area, you can simply pick like a small, you simply integrate, but if you go to the more detail that from the scratch, in the beginning, you're going to pick like a small strip with the infinitesimally small width, extremely small width dx. Okay, if you go this way, if you take like a vertical strip, you're going to pick like a infinitesimally small width dx, or you can go this way, horizontally or vertically, you can get this done. But if you do vertically this way, you can easily stack those strips on top of each other to sweep out this whole area. That's how you're going to find the area under the curve. Pretty much the similar fashion, you can do with the aid of the horizontal strip, you can stack all the way up to here, but you got to be careful, because that when you pick a strip over here, it looked like a very rectangular, but once you pass this point, it's going to change. So that means if you do that way, you have to divide this into 2 portions. See? one set here and another set here, okay? So I'm not going to go ahead and then look for that area under the curve. What I'm trying to say that if you get the area and rotate about this axis, and once you rotate this area about this axis, y-axis, that would sweep out a three-dimensional solid figure with something hollow in the middle. See, it looked like something like this. See, I'm not going to draw this to a scale, but see, you have the same thing on this side. See, like this going to be x equals -1, this going to be x equals -2. See, rotate, and here you're going to have some kind of a cylindrical shape. Even on the top, you have something like that. See, that's kind of a three-dimensional figure you're going to see at the end of the day. If you really want to find, this is hollow, okay, there's nothing over here, only the shaded region has something, okay, it looks like some kind of the ball outside, see, you have like a cylindrical shape, you have taken out this ball, it looks like that, see, taken out the ball and the leftover we are looking into. In such a scenario, if you really want to find the volume of the shaded region means not only this one, the three-dimensional, okay? That one, these are hollow. See, it looks like a ball over here. It's a cylinder. How could you gonna find the volume? If you use the shell method, you're gonna pick a shell at a certain point. In the shell method, if this is the axis of rotation, you're gonna pick small strip, see, small strip on this area. Don't worry about this one. Let's get back to this area under the curve. This area, small strip. Why it's go this way, horizontal? Because if you are planning to use the washer method, you have to have that strip perpendicular to the axis of rotation. Axis of rotation. This is axis of rotation. This strip has to be perpendicular to the axis of rotation. See, axis of rotation. See, that's why we took this way. We might be thinking why we cannot get this way. No, if you take that way, then you're going to jump into the shell method. Yeah, I'm using the washer method. Okay, I'm trying to create a washer method. In washer method, okay, washer method. In washer method. Okay, in washer method, you have to make sure your small strip has to be perpendicular to the axis of rotation. Okay, I'm talking about this one. Then you take that one, and if you rotate with the thickness of dy, okay, with the thickness of dy, at which point? At a distance from, if you want, you can say distance from here to there. Okay, that would be your x all the time, doesn't matter. Okay, or if you want, you can put this one as a your x. See, at this point, this point, this point, the x getting changed. If you want, you can put that one as x. Okay, doesn't matter. See, the point would be at that point. For your convenience, I'm going to say at the point of x, this height would be y, and this is same y and dy, thickness dy. See, this would be your general point. See, general point, general point, general point, point. See, anywhere you can get this done. Okay, for my convenience, I took only over here. Okay, see, this one. See, then again, since I said earlier, since you're that shape gonna change at that point, you have to do this one again for this region. That means you have to separate this into two parts, okay? One from here to here, the other one from here to there. Okay, see? But still, this one is my general point. General point distance from the rotated axis of rotation to the general point would be the horizontal distance x, vertical distance y, same thing. See? But when you do that washer method, you use two regions, okay, from this point to that point, one integral, the other integral from here to here, because of the non-uniformity of the shape. I'm talking about this shape, okay? See, they're gonna change. But you don't have that situation here, okay? Then let's say that you are trying to put over here, that for your convenience, we are here, see? Again, this is y, this dy, see? This point is, see, at a distance of x. Then if you rotate this one is very easy, because you know that if you're gonna stack this kind of a horizontal strip on top of each other, that would create some kind of like a hollow cylinder. That, forget about that part. In this part, from going from here to here, you're gonna have a, see, washer like this, see, with a thickness of dy, see. So this axis of rotation. So you have something like this and something like this. So that means you have a, for this washer. Then later on, what are you gonna do? You're gonna stack washers from here to here, here to here, okay? When you do here to here, done, here to here, okay? So when you stack them, that would cover pretty much the whole region for which that we are eyeing for the volume. So look at this one, this height is this one. I'm gonna call this one, since washer, the inside radius is Ri, outside radius is R naught, see? Ri and R naught. It's not, see, different notation, R prime, simple R prime. Here, Ri, R naught, see? So in a similar fashion, see, you saw that what we did over here. This is how we're gonna do when you've been given like some kind of a curve. Curve being rotated, okay? Curve being rotated. The area under the curve being rotated around about a certain axis, and that would generate a three-dimensional figure, and then its volume we are looking for. So this is how we're going to use the washer method. Then you can easily find the volume of the washer, and then you're going to integrate from that point to get that volume, and separately you do that one more time from here to here, okay? So similar setup we can apply here. Here, the major difference, here we don't have an equation like this. No equation. Look at this, the difference. The equation has been given. You know that once the equation has been given, doesn't matter with respect to y or x, you still can integrate. If you want to integrate with respect to y, all the x terms been replaced in terms of y, and then integrate with respect to y. Or vice versa. If everything has been integrated with respect to x, then all the terms in that integrand has to be in x. And if you see any y term can be easily replaced, because there's a relationship between y and x. But there's no such thing here. Here already that the three-dimensional figure has been generated. There's no equation for either for sphere or cylinder here. Take the difference. Just get clarified over here, get a clear-cut idea that what's going over here. No equations, okay? You are familiar with that, we deal with the equations and the integral, but still we do the integration here. But we tackle different way. The three-dimensional figure has already been created. And with the aid of what's being given, only thing this guy or this guy and this guy or this guy, the same thing being given, that's all. You have to find the volume, the same thing like that, okay? Pretty much the same thing like that, see? So if you encounter that kind of a thing, we can tackle later. But here, since we are dealing with a little bit harder one, first, for a certain reason, to lay down a foundation for you to, because these are the kind of a question you are struggling with all the time. That's why I chose this one. So same like earlier, let's say this is my axis of rotation. From that one, I can easily pick a general point somewhere at a distance of x, see? distance of x, and the height would be y. See, look at that. With a thickness of what? dy. See, I pick a vertical, see, sorry, I pick a horizontal strip. See, horizontal strip. It's going to start from here, okay? Start from here, or if you want, you can start from there. It doesn't matter. If you don't like this one, you say at this point, okay, this is your x. Doesn't matter. This is your x. This is your y. Doesn't matter. See, doesn't matter. And with the thickness of this is my strip. See, right here, consider an infinitesimally small, very small, horizontal strip of, see, no, this area there's nothing, okay? I'm going to consider only that strip with the material. There's no material here, okay? Strip of width of d with dy. You know the reason that why we pick this horizontally. You know the reason. If you want, you can go this way, then we're going to end up with the shell method, okay? This method, because this is perpendicular to the axis of rotation, see, axis of an infinitesimally small horizontal strip of width equals dy. That strip has some length, okay? I would say if you're going to take that out, see, from here to here, that's the inner radius. Inner radius, I will denote by inner ri, which is x in this case, see, inner radius ri, and outer radius, which is denoted by r naught. Outer radius is how much? R prime, see, R prime. See? That would be R prime. Outer radius. R prime. R prime. Capital R prime. See, R prime at a distance x from the y-axis, which is axis of rotation, perpendicular to y-axis, axis of rotation. See, strip. Or you can say that consider an infinitesimally small horizontal instead of strip. You can think about that if it is rotated, when it's rotated, it's already rotated, okay? You don't have to talk about that. When it's rotated, that would generate definitely a shell, washer, okay? Washer. oh, sorry, this one, outer radius, this one, outer radius, I'm going to denote this way for your convenience. Okay, this is x. Okay, r naught, this one ri, ri the same thing. Ri, this is not that, sorry, it's not that, r naught, because it's not this length from here to here, not the same as, this is r naught. This is x. X is nothing but simple ri. See, same thing. Okay, I can add something here. Simple ri, simple r prime. Sorry, simple r prime. Same thing. This length is r prime. It's the inner radius of the strip. The outer radius would be different, not this one. Sorry, not this one. See, inner radius would be inner radius. I'm going to denote by ri, which is x in this case, plus r prime in this case. Okay. R prime means the inner radius of the, you see, the radius of the cylinder is same as the distance x, okay, and which is also denoted by ri. It's just a label, okay. Then the r naught, we don't know. R naught we have to find out, okay. R naught we have to find out. R naught we have to find out in terms of what's being given from these terms. See? These terms, that's it. But the inner radius has been given in terms of something being given, okay. So then what happens? When this strip is rotated, it's already done, okay. I'm trying to show you how this can be generated, okay. When this strip, when it is in this strip, say it's rotated about the axis of rotation, which is y-axis, y-axis, a washer of thickness dy, inner radius is ri means x, x means r prime, and outer radius, which is r naught, will be swept out. Okay, then let's draw that one, okay. I'm gonna draw that. I'm gonna draw that washer. So that's what we were talking about, like this, like this, like this one. I enlarge, okay. I'm gonna enlarge for your convenience. See. That's the washer. See, I enlarge. Okay. So this is the axis of rotation. axis of rotation, y axis of rotation. From here to here radius, you can remember, I denote that by Ri, or which is x, which is r prime. The other radius, okay, somewhere to here, outer r naught, this thickness dy. How do you find the volume of this one? You can find the volume, but the problem is that when you find the volume, everything has to be written in terms of what's been given. This part is okay, but we have an issue with the R naught. Let's try to find out R naught in terms of the rest, okay? Let's try to find out. I'm going to little bit erase this one, this one, this one, and this one, this little bit erase, and then I'm going to write it down everything clearly again, okay? So we call this one R naught, this length, okay? This is my interest, R naught. But I know this length is nothing but the radius of the sphere, which is R prime, capital R prime. I know this length from here to here, Y. You see? Now I have a triangle, see? O, A, B, right triangle from you can say 4 OAB, right triangle. I'm going to write the right triangle right rather than writing. I'm going to draw this one triangle using the Pythagoras theorem. Pythagoras theorem. Theorem I can write as an abbreviation. Theorem like that. Okay, it's an abbreviation. Theorem, you can simply say, okay, theorem. I'm going to write this down here. Okay. We know that OB squared, the hypotenuse squared, equals the sum of the other two sides. This one is R prime squared, AB squared, R naught squared, plus this one, Y squared. Okay, therefore, I'm going to use these three dots at vertices of a equal triangle. That's a notation, okay, later on. So R naught squared equals nothing but R prime squared minus Y squared. Therefore, R naught is some square root of R prime squared minus Y squared. y squared. See? Now it has been given something like that. It doesn't matter because our operator is dy. Because of that, terms come in y, it's okay. Now we can find the volume of this shell, the washer. I'm gonna find the volume of the washer. How do you find the volume of the washer? Volume of the washer. I'm gonna denote by dV, infinitesimally small, dV. dV is nothing but cross-sectional area times the height. See, cross-sectional area times height. Height is the width. See, this width. How do you find the cross-sectional area? See, it's a circle. Outer circle area minus the inner circle area, because there's no contents or the material in this area, okay? So pi r naught squared minus pi r inner square times dy. See? I'm talking about this cross section. Cross section means that's the section that is the profile that is, or side that is common to the whole region. See, the cross section. So then we can plug in whatever we have over here. Okay. So I'm gonna erase this one and try to find dV. Let's write dV. Okay. This dV. dV, I'm gonna pull out pi, then you get r naught squared minus ri squared dy. Then let's plug in whatever we have. R naught squared means r squared, r prime squared minus y squared minus y squared. See, is that right? Because this one has to be square root, has to be square minus ri is nothing but x squared. Can you remember? dy. X is nothing but simple r. So pi, the square root and they get cancelled off. You are left over with this minus r times. I replace x with r, simple r squared. You can remember that. Then I can put the constant terms together. This is a constant minus this is a constant, see, and minus y squared dy. See, that's the volume of the that's washer. Okay. Volume of the washer. Now what? We're gonna stack those washers from where to where? From here to here. See, if you stack from there to there, that would cover the volume of the bead. See, I'm going to a little bit erase what I had earlier, and then I'm going to draw what I need right now. See, I need this point to that point, or at least one side if you can find it. In that way, we are in good shape. What that point would be in this length. I'm talking about this length, not this length, because I'm trying to do the integration with respect to y in this direction. You pick that one, pick this strip horizontal strip which is perpendicular to the y-axis. So I'm going to integrate in this direction. To integrate, see, you need this is a washer. This is a washer we had over here. Can you remember? This is the washer we had. See, dy, see, this inner radius, outer radius. So I'm going to stack those washers from where to where? This point to that point. Can you remember this one is nothing but, see, this point, you know those points, okay? To that side or this side, doesn't matter. I'm not going to draw too many of these because to mess up this one. But anyhow, I'm interested on this one. Look at how could you going to get that one? This height, oh, see, I'm talking about this height. See, this point, you know this one, R prime. You know, let's say H. See, I'm going to do this one on this side, okay? Doesn't matter any side, okay? That's what, capital R prime. That's the radius of the sphere. This is the radius of the cylinder. Now we have another one. See, I'm going to call this one ABC, AOBCD. See, it's a right triangle. Again, with the aid of the right triangle of OCD, I can find H. That's the same H on this side as well, okay? So now you know the Pythagoras theorem. You can easily utilize Pythagoras theorem for this one. See, for OC for OCD right triangle using the Pythagoras theorem, we have we can say OD squared equal to OC squared plus CD squared. See, the square of the hypotenuse is same as the sum of the squares of the other two sides. So this one is R prime squared. This OC is H squared plus this one is simple R prime square. See? Then you can easily find H. Therefore, H would be H squared. Therefore, now you are familiar with this notation. R prime squared minus simple R squared. Therefore, H square root of R prime squared minus R squared. Actually, you're going to have a plus or minus to indicate this side and that side, okay? You can put it like that. Okay. See? That's H. So this point, see, this H is that much. So you can easily integrate the shells from here to here. That means minus H to plus H. Therefore, let's go back to find the volume of the bead. Volume of the bead is nothing but volume of the bead. Volume of the bead. Bead is nothing but the sum of volumes of washers. Washers from minus H to plus H. See? That means V of bead is nothing but integration, because they were stacked so closely each other, we're not going to use a summation. Here summation has, we don't need, because they were not discretized, they were continuous. So I'm going to integrate my dV. So integration, you can remember, it's going to go from minus H to y equals H to y equals minus H to plus H of dV. dV we had earlier, dV is this one. R prime squared minus simple R squared minus y squared whole thing dy. I hope you can see. Dy. Can I erase this? Oh, no, we need this one. I'm sorry, this R prime squared. Okay. So we can plug in this one later on. Let's do the integration first. Okay. So that means another way, V is nothing but integration y means this square root this one r prime squared minus r squared to okay r capital R prime squared minus simple r squared r prime squared minus r prime squared minus y squared dy. See, that's the integral. So we bead. And let's integrate. Very easy. These are constant, okay? Constant, constant, constant is the variable. So V bead is nothing but constant times y when you integrate. This one becomes third over 3. And you're going to plug in your r prime squared minus r squared to this one minus, okay, minus r prime squared minus r prime squared. That's it. We're pretty much done. See? Then plug in upper bound and the lower bound. That's it. Okay. Then let's plug in this one here. V bead equals r capital R prime squared simple R prime squared times y mean this one R prime squared minus this one. Okay. Then minus 1/3 y cube. Cube means this one, this is y, minus this one cube. That's the first set. first set. The second set, you're going to plug in negative value for here, r prime squared minus this one, negative of capital R prime squared minus simple r squared, close it, minus 1/3 negative r prime squared. See. Then I put the upper bound here, then put the lower bound. Then okay, for your convenience, what I'm gonna do, I'm gonna say this is plus h, okay, easy. I keep with the h, go with the h, okay, h cube. This one minus h, this one minus h cube. Okay, let's go like that. It's easy. Okay, then you don't have to struggle too much writing this. Okay, this one r prime squared h minus 1/3 h cube. See, minus minus plus. Okay, minus minus plus. Then r prime squared h. Okay. Then minus, this one become minus again, minus minus plus, plus time minus, minus 1/3 h cube. Is that right? I put the upper bound, going from capital H to simple, see, going from positive H to, see, going from this side to that side, negative to positive, okay, negative H to, going, I stack from here to there, okay, negative H to positive H. Okay, that's why when I integrate for the lower bound, negative H, upper bound, positive H. Upper bound, I plug in here to replace Y. I plug in here for the lower bound, see. So you have minus 1/3 h cube, r squared minus plus plus minus. So here we have 2 times r prime squared h, no? Here 2/3 of h cube. Two-thirds of h cube. So this one, then you're gonna plug in r prime squared minus r squared square root H means r prime squared minus r prime squared minus 2/3 h cubed r prime squared minus simple r squared whole thing cube. Then V bead. See, the same thing here, 1/2 power is 1. You can combine 2 of r prime squared minus simple r squared. You have a 1 from here, half from there. See? Plus, minus, sorry, 2/3. Same thing, r prime minus this one squared see here 1/2 times 3 on the top. So 2 r prime minus, look at that, final answer being written in terms of what's been given. You don't need the equation of that sphere or that any the cylinder. Here 2/3 r prime minus simple r prime squared 3/2. See, 3/2 and 3/2. I can pull the common term out. I can pull 2 I can pull r prime squared minus r prime squared 3/2. Let's see what's the leftover. Leftover is 1. When you pull out 2 and this part from that one, you left over the 1. 1/3. 2 r prime squared minus r prime squared 3/2. Then let's simplify. 3 minus 1 over 3. See, 3 times 1. See, if you got 1/3, that's 3, 2/3. Okay, so here 2, 4 over 3 r prime squared minus r prime squared 3/2. Somewhere I think we missed pi. Okay, pi. I missed the pi. Pi. 4 pi over 3. So now they ask for the when capital R equals two and simple R equals 1. Let's plug in. V bead nothing but 4 pi over 3 r prime squared, capital R prime squared, which is 2 to the second minus 1 to the second 3/2. No, we didn't do that one. Not right, because the when this one we have to create this one. R prime is 4R, simple R prime is 3 simple R. 4 times 2, sorry. 8, 3 times 1, 3. Now you have to plug in that one. And for me, this value is gonna, see, this is the final answer. In algebraic answer, this one, see, that's the algebraic answer. If you need the numerical answer, you have to get the aid of capital R equals 2 means R prime equals 8. Simple R equals 1 means R prime equals 3. So 4 pi over 3 R prime is 8 to the second minus 1 to the 3 to the second, and 3/2. This one, 4 pi over 3, 64 minus 9, 3/2. Therefore, final answer should be 4 pi over 3, 55 to the power of 3/2 times 4 pi over 3. See? If you get this done using the other method, shell method, that means that picking that the strip vertically, you're going to stack. If you rotate, you're going to have a shell. Those shell will be stacking from this point to that point, and then that will cover the whole volume of the bead. Okay, so we can talk about that one next time. Until then, I'm going to give you a break, because that I know you have, the brain is already swollen, already full of all kind of stuff. And then especially something like this, if you're going to get for the test, make sure just do like this, but you need the practice. Okay, with all this practice and everything, pretty soon I'll be back to you with the other method, which is the shell method, in another video. Until then, you guys have a great day. Good luck, and wish you all the best. Be safe and be healthy, and take care of yourself. Okay, thank you. Bye-bye.